Yeah, my name is Amanda Cook. I'm here to tell you about one of several lunar instruments that we're developing at NASA Ames. And this talk is about one that we call Moon 3D, which is a 3D depth mapping camera that we matured with our flight instrument group at Ames, which we affectionately call FIG. Next slide. So the Moon 3D instrument project is comprised of several collaborators, and I won't have time to name them all. A large group of us is, again, from NASA Ames and all from our FIG flight instrument group. We have a very close partnership with the scientists and developers from the Space Exploration Initiative at MIT. And we've also spent a good amount of time interacting with some excellent people from Lunar Outpost, which is a commercial lunar rover company based in Denver. And I realized after submitting this presentation that I neglected to include important members of our science team. And this is what you get when an engineering-focused person makes a presentation, huge faux pas. But our science team includes Paul Hain at LASP, Maria Banks at Goddard, and Jennifer Lopez with Odyssey Space and National Geographic, as well as David Newman from MIT's Space Exploration Initiative. Next slide. So throughout this presentation, I'll be referring to two missions, and there's quite a bit of overlap in terms of scientific content, but the camera I'm going to tell you about is already integrated on Lunar Outpost's MAP-1 rover, which is labeled 1 at bottom left there. And you can see it there in this rendering of the Intuitive Machines lander, IM-2, which launches early next year now. And the rover is deployed to the surface there inside a so-called garage. We can see kind of covered in this copper MLI. And the rover carries several small payloads, including our camera. And so that little gray arrow is pointing to a closer view of the rover. And you can just see our camera looking out the front panel. So for reference, the rover there is about the size of a beach ball. And on the right here, labeled 2, is our upcoming target opportunity, the Artemis 4 human mission to the moon. And as part of the Artemis 4 deployed instruments call, we plan to propose a modified and supplemented version of Moon 3D as more of a dust payload suite. So I may be kind of unintentionally switching back and forth between these two missions, and kind of for shorthand, I'll be calling them Lunar Outpost or Artemis 4. But the instrument I will be focusing on here is a time of flight 3D depth measurement camera that includes RGB and NIR imaging at 850 nanometers. And this instrument, just that camera, is the one that's already integrated on the Lunar Outpost rover. And like I said, we'll propose a follow-on instrument suite for Artemis 4 that includes not only this 3D imager, but also a particle impact sensor and a nephelometer to measure backscattering from lofted grains. Next slide. So with just the 3D depth camera and visible near-infrared imager, we're pointing ourselves toward a particular science focus. The Moon 3D science themes are, of course, derived from the goals identified in the Artemis 3 science definition team report. Our measurements kind of focus on to answer questions about regolith processing, volatile retention, and of particular importance to this workshop, exploration factors related to both lander plumes and astronaut EVA activities. So as this audience knows very well, regolith processing includes solar wind processing, as shown here at the left, but also micrometeorite impacts, thermal cycling, and other processes. And so at the left, I'm showing some really cool electron microscope images of lunar grains from Denevi et al., where the effects of grain weathering are visible both at the outer rims of the grain and internally as a result of solar particle strikes. And using visible and near-infrared imagery of regolith, for example, we look at landing site areas with regolith like this and measure its optical maturity properties. And we can do this at areas closer to the landing site and further away. And since the plume will likely scour the nearby landscape, we intend to measure transects with distance from the landing site to measure optical maturity of the intact versus the uncovered regolith. And with 3D maps of local topography, we're also able to get a view of the small scale effects of micrometeorite impact processes. We're targeting the measurement of the size distribution and the spatial distribution of micro cold traps near the landing site, again, in particular as a function of distance from the landing site. So this provides a map of the areas that have the highest potential for volatile retention and helps us understand how the landing itself will disturb micro cold traps in the immediate area. So combining the maps of the cold traps with the multi-wavelength imagery, we can begin to understand the relationships between micro PSRs and regolith processing in those environments. And lastly, with astronauts interacting with surfaces in our field of view, we can characterize many characteristics of the regolith by examining astronaut boot prints, for example. And that will help us, just as it did in Apollo, will help us quantify regolith density, cohesion, other factors that would be relevant to planning, for example, dust mitigation for future missions. I've decided to skip this slide, this next slide that says Moon 3D Science, because I'm already kind of covering it in the slide before. And considering my, more focused perspective on instrument development, I wanted to kind of show you how we arrived at this instrument. So here is the beginning of the instrument that we developed for the Lunar Outpost mission. So MIT proposed to fly a Microsoft Kinect on board the Lunar Outpost rover and came to our group at Ames to help with ruggedizing and optimizing the camera for space. And our group is finding more and more that making use of commercial products can lead to much cheaper and much smaller instruments with a low effort to do this ruggedization and optimization. So typically with some simple modifications, we can make these instruments more relevant to the types of measurements that we're targeting. So you can see the Kinect is a small device fitting in this guy's hand. On the left of that device in that left-hand picture is a lens for the RGB camera. The middle lens is the NIR camera. And on the right of that sensor head, the next sensor is invisible under the glass window, but it's actually the near-infrared source for the time of flight sensor. So a pattern of near-IR light is projected out onto the surface, and the time to reflect back and return to the sensor is recorded and generates a 3D map of the scene. So very important for making these measurements at the moon, this sensor can operate in the complete absence of light. So we don't need to bring an additional light source. It's already on this sensor. And it will allow you to see into the shadowed region of small PSRs at the landing site or cold traps. And at right, you can see an exploded view of the Kinect showing the various internal parts. And optimize for mass and volume, we removed a significant portion of the structure, removed the microphone arrays, removed cover glass, etc. So I'll get a little bit more into the details here on the next slide. So this is our instrument development. So this is a peek at what the process looked like. So at upper left, you can see that we've disassembled the back end of the Connect device. And there's an aluminum enclosure that holds the electronics board. And we completely redesigned that structure to what you see at bottom left. And so basically the board instead sits on a very small backplate with a rounded square that is used as an interface to the rover panel. And at the right, you can see our modified Connect integrated at the front of the rover. And again, that rover is roughly the size of a beach ball. Next slide.
Hi, Amanda. We need you to wrap up. We're already over time.
Oh, goodness gracious. Thank you. Let me just skip to slide 10 then. I would just say that next one. What we're in the process of now is actually doing a camera trade study because the Connect was discontinued. So we are looking at new cameras with better capabilities. And I'll leave it at that. Thank you. Sorry for going over.